Good morning. This is our story of how we progressed an idea for a new on-site wastewater treatment system using science and engineering. The FlexTreat Biofilter provides another option for replacing these archaic cesspools that currently don't remove nitrogen. So, this is our story. Back in 2016, the center realized that we needed to build a research facility. So working in harmony with Suffolk County, in particular Peter, we were told that Suffolk County Sewer District number 10, which is just south of the campus on a side road, Parson Drive, at the intersection of Stony Brook Road and Route 347. The area that we were given, is shown in the white box. And that's our wastewater research and innovation facility. So this is in 2016, way before I showed up, way before we really started getting going with the experiments. So this is a blow-up of that white box that you saw. We actually did this in 2 phases, building the research facility. The first phase were trailers where we put in column-sized experiments, maybe 50 gallons or so. You could see that picture on the bottom right. Phase 2 was the build-out of what we call the backyard. And here's where we put the full-scale prototypes, or like Stewart's experiment with retrofitting cesspools, and also FlexTreat, which is shown there at the bottom. So the idea, let's use an equalized aerated continuous 24-hour flow with attached biological growth to nitrify. This process should recycle nitrates and use wood chips as a carbon source that supports an environment where denitrifying bacteria thrive. So it's based off of the nitrogen removing bioreactors, but we shrunk it big time. So what are our new objectives for this process? The first is it has to be affordable and comparable to other IA systems, otherwise it's never going to be used. Similar footprint to other IA systems, so we can build on smaller lots. We get homeowner acceptance, and also the smaller it is, generally the less costly. It has to average 10 milligrams per liter, not 19 milligrams per liter, which is the county standard. Has to be plug and play, factory assembled and tested to minimize field labor costs. By testing in the factory, we eliminate a lot of the hiccups that occurred during construction. And it has to be flexible, flexibility to adapt to changing wastewater strength and flow. The flex part of that is where FlexTreat comes from. It has to be easy and inexpensive to operate and maintain. So unlike other systems which have a lot of operator attention, our goal was to keep operator attention at a minimum. And we decided at that point, let's call it the FlexTreat Biofilter. So the project progression, in February 2018, the research facility started construction. You could see what the trailers look like there. Then in October of that same year, the backyard expansion started. So we were concurrently doing phase 1 with phase 2. Then in the summer or fall, we had to take all that material and load the columns, and also the students and the researchers needed to be trained on this new facility. So So once that was done, let me go back here one more. Yes, so in the summer fall, we also installed the pilot program or the pilot system, which now Siwei will discuss.
Okay, so thanks, Frank, for sharing the general idea of the FlexTreat biofilter. So nextly, I will talk about how we develop a pilot scale system to verify the design and idea of the FlexTreat biofilter. This slide shows the design for the pilot scale FlexTreat biofilter. It comprises a pump tank, a nitrification column, an intermediate denitrification column, and a final denitrification column. The nitrification column is filled with 100% of the sand, and it can convert the ammonium in the raw wastewater to the nitrate. And it can also do the organic matters decomposition. And for both of the intermediate and the final denitrification columns, they are filled with 100% of the wood chip, and it can convert the nitrate generated in the nitrification columns into the nitrogen gas to remove the nitrogen from the wastewater. And also, the wood chip can provide long-term carbon source for the denitrification. For our FlexTreat biofilter, it has 3 unique features. Firstly, it has the continuous flow pattern, so that can keep the constant water content at the surface of the filtration media, which can promote the growth of the microorganism. And secondly, it has the internal recirculation pattern, which can recycle the effluent from the intermediate denitrification column back to the pump tank to increase the detention time of the nitrogen and increase the treatment performance. And thirdly, it has a pre-aeration system. So we have an air pump, which can aerate the mixed liquid in the pump tank before it enters into the nitrification columns, so that can compensate the oxygen loss caused by the nitrification and the organic matter decomposition processes. So we constructed our pilot-scale FlexTreat biofilter in the Water Research Innovation Facility. And we have 2 white barriers for the nitrification columns. We have 2 blue barriers for the intermediate denitrification columns, and blue barrier for the final denitrification column. The right graph shows the engineering design for the pilot-scale FlexTreat biofilter. So we currently operated the FlexTreat biofilter for over 3 years. During this year operation, we stepwise increased the nitrogen loading rate, hydraulic loading rate, and the recycle ratio to test the optimum operational conditions for the FlexTreat biofilter, and the result is shown in the graph. So here we can find the black line represents the total nitrogen concentration in the influent wastewater, and the red line represents the total nitrogen concentration in the final effluent from the entire system. And 10 milligram per liter is our treatment target. 90 milligram per liter is the discharge limit of the nitrogen regulated by the county. So here we can find, even operated at high hydraulic loading rate of the wastewater, which is around 4 gallons per day per square foot and recycle ratio of 3, the FlexTreat biofilter can reduce the total nitrogen concentration from over 70 milligram per liter in the influent wastewater to around 30 milligram per liter in the final effluent. That's a very good treatment performance. And if we compare the FlexTreat biofilter with other conventional biofiltration system designed for the on-site wastewater treatment, we can find the FlexTreat biofilter can achieve most efficient total nitrogen removal efficiency at highest hydraulic loading rate. For the recirculating sand filter, nitrogen removing biofilter, and the constructed wetland, they require high footprint to accommodate the low designed hydraulic loading rate. And for the hybrid absorption and biological treatment system, even it can achieve efficient nitrogen removal at a relatively high hydraulic loading rate, but it's still lower than the FlexTreat biofilter. It uses the elemental sulfur as the electron donor for the denitrification. So it can generate the sulfate in the final effluent and cause some adverse environmental impact. So based on this graph, we can find the FlexTreat biofilter is the winner over other competitors. However, just like other biofiltration systems, the FlexTreat biofilter has the clogging problem when it's operated at the high hydraulic loading rate. We think that's majorly caused by the small particle size and the low porosity of the sand in the nitrification columns. So we want to explore the alternative materials with higher porosity and bigger particle size to replace the sand and elevate the clogging problem. So based on the literature review, we selected 4 potential filtration materials: the gravel, marble chip, zeolite, and biochar. At stage 1 experiment, we set up 4 columns in our research trailer, and filled with the combination of the sand, gravel, marble chip, and zeolite to explore the optimum major filtration material. And finally, we then identified that the marble chip and zeolite, they can achieve most efficient ammonia removal performance and with the limited clogging problems. So they are the optimum major filtration materials for the nitrification columns of the FlexTreat biofilter. So at stage 2, we amended 30% of the biochar into these 2 materials to test the feasibility of the biochar amendment to further increase the treatment performance of these 2 materials. And the result is shown here. So here, in the left graph, that shows the treatment performance of different material at stage 1. So we can find the zeolite and the marble chip, they can achieve significantly higher ammonia removal efficiency compared with the sand and the gravel amended sand columns. So based on this result, we identified that the marble chip and zeolite, they are the best major filtration material for the nitrification columns of the FlexTreat biofilter. So at stage 2, we just amended 30% of biochar into these 2 materials. And here we can find the biochar amended zeolite column achieved similar level of the ammonia removal efficiency compared with the pure zeolite column. However, the biochar amended marble chip column achieved significantly higher ammonia removal efficiency than the pure marble chip column. So this result indicated that the biochar amendment can increase the ammonia removal efficiency in the marble chip, but has no impact on the zeolite. Besides the ammonia removal performance, we also calculated the dissolved inorganic nitrogen concentration in different columns to evaluate the contribution of the nitrification and absorption to the ammonia removal in the zeolite and the biochar. And finally, we found that, okay, the nitrification contributed to over 85% of the ammonium in the removal in the zeolite and biochar. That's very good news because that indicated that the zeolite and biochar can achieve long-term ammonia removal with limited maintenance demand. Besides the treatment performance, we also evaluated the hydraulic performance in different materials. So during our around 6 months experiment, so the sand column and the gravel amended sand column clogged every 1 to 2 weeks. However, for our marble chip columns and the zeolite columns, we never observed any clogging problem. So collectively, this result indicated that the marble chip amended with 30% of the biochar and the zeolite with higher porosity and big particle size can significantly elevate the hydraulic challenge of the biofilter and achieve very efficient ammonia removal performance. So nextly, Frank will talk about how we upgrade the pilot scale system to the full scale system to test the FlexTreat at the real condition.
So based on 2 years of solid science by Siwei and his advisor, Dr. Chen Mao, we had the concrete proof that FlexTreat worked and was viable. This gave us the data we needed to convince SUNY Research Foundation that they should continue to invest in the technology and proceed with the patent application filings. So the project progression continues. So in December, you see there, 2019 to April 2021, the FlexTreat biofilter prototype was delivered to the site and installed. The construction of the backyard continued now that we had the prototype. You could see the installation on the bottom 3 slides as completed. So in October of 2022, the prototype started treating wastewater. In December of just last year, the patent was issued, again, based on the work that Siwei and Dr. Mao. So the nitrogen, we started getting great results in April of 2024. We had taken the system down, cleaned it out, started all over again. That's the beauty of the research facility. We're able to do that. We swapped out the media from sand to marble chips based on the research that Siwei just talked about. And so now it's just a matter of monitoring performance. Tom Volley, who just joined the center last year, and we have over 85 years of experience in wastewater systems, so we're having a blast. Really good time. I think I speak for Tom when I say that, and thank you, Tom. So how does it work? The home is on your right, and the septic tank is on your right. So I'm going to read this. Wastewater flows by gravity from the house to a septic tank where solids and sludge are captured. This flow is termed 1Q, or the average daily flow. The septic tank effluent flows into chamber number 1, that's those circles there, which equalizes the flow and organic load over 24 hours. The septic wastewater is also aerated to supply oxygen. The oxygen-rich wastewater is then pumped at a controlled rate to chamber number 2. Chamber number 2 is the nitrification chamber and provides the media and the environment to support nitrifying bacteria. The flow is downward as it converts the ammonia to nitrates. The nitrified flow is split. 1Q flows to nitrate polishing, those wood chip boxes that Stuart talked about. The flow is downward, okay. Split 1Q of, 2Q is then dumped into chamber number 3, which we call the anoxic chamber. This is, the anoxic part is we deplete whatever oxygen remains after nitrification, because the next step is denitrification, which occurs in the absence of oxygen. So having a residual oxygen actually hinders the denitrification process. So we get it down to near 0 at this point. The nitrate-rich 2Q overflows into chamber number 4, known as the denitrification filter. This chamber is where the system takes a final step in eliminating harmful nitrates. Wood chips support denitrifying bacteria, provide a carbon source, and provide the required detention time for converting the nitrates to harmless nitrogen gas. The water level in the denitrification filter is maintained in a submerged condition by regulating the water levels in the pump tank, because denitrification takes place in the absence of oxygen. Denitrified flow is combined with the household flow from the septic tank. Again, the flow is constant throughout the day, including when residents are asleep, and flow is 0. So these are the where we are as of today. We're currently treating about 230 gallons per day, but our target is 440. And that's the beauty of the prototype, is that we can do things to enhance performance while also increasing challenging the system to work under higher flows. The nitrification surface loading rate is 14.3 gallons per day. You heard from Siwei, the columns were at 2 to 3 gallons per day per square foot. So that's roughly 19 times smaller than what the current NRBs, nitrogen removing biofilters, are doing. And warmer month performance, no surprise, is around 10 milligrams per liter of total nitrogen. Oh, wrong one, sorry. So this is the results of a full-time online nitrogen sensor, courtesy of Dr. Zhu, who invented it here at the center. That's him. So this data is over 2 years, and this line indicates the total dissolved inorganic nitrogen, which is the ammonium plus nitrates. we also have an ELAB certified laboratory right here run by Caitlin Asado, who I know is here as well, and her staff. And you could see that the data correlates perfectly with the nitrogen sensor. Just to point out, we're just recently, April, we had the 10 milligrams per liter. The little blips, those are self-calibrations. So try to ignore that. So what's next? Well, Tom and I will monitor the performance on steady state. We'll try to make those improvements to increase the flow. Also, right now we're treating about 60 to 70 milligrams per liter of TKN, and our goal is to try to get it up to 100, which is seen sometimes. We'll be able to do that by artificially adding nitrogen to the wastewater. We'll make those system enhancements to improve performance and O&M. Then we have to design prototype number 2 and have that factory assembled, mimicking exactly what the real world will be once we go into commercial operation. And our goal is to enter Article 19, which allows us to put in experimental units and ultimately come to the general use of the FlexTreat in Suffolk County. So with that, thank you for being here, and I would also like to take this opportunity to thank my co-workers who publicly want to thank because they are exceptional. And thank you.